From the moment the James Webb Space Telescope settled into its orbit at the second Lagrange point, roughly 1.5 million kilometers from Earth, astronomers anticipated breakthroughs that would redefine modern astrophysics. What no one expected was that one of its earliest deep-field observations would reveal something so strange that it defied classification, sparking urgent debate across every major research institution. The discovery began not with dramatic fanfare, but with a routine analysis session at the Space Telescope Science Institute in Baltimore, where teams were reviewing infrared data from galaxies located over 11 billion light-years away. These early observations were intended to test the telescope's stability, but buried within the data was a signal unlike any recorded in decades of deep space research. If you thought deep space had given up all its secrets, think again. JWST has revealed a mysterious object that doesn't fit any known cosmic category, and scientists are racing to understand what it could be. Subscribe now as we start our journey. The object first appeared as a faint point surrounded by an unusual gradient of infrared intensity. Analysts initially tagged it as a red dwarf star or perhaps a compact galaxy, but the light signature did not match either. It emitted less visible light than a typical star, yet more infrared radiation than a cold object should. The ratios of its emissions seemed unbalanced, almost curated, with distinct patterns that did not resemble natural spectral noise or standard cosmic dust absorption. Over the course of several days, astronomers ran additional filters through JWST's near-infrared camera and mid-infrared instrument, trying to rule out sensor anomalies or calibration issues. They cross-referenced the coordinates with the Hubble Legacy Archive, the Sloan Digital Sky Survey, and the FIRST radio catalogue. The sky at that location had always appeared empty. The first clue that this object differed from known categories came when the photometer detected a thermal signature far too stable for typical astrophysical processes. Most stars fluctuate in brightness due to convection currents, pulsation cycles, or magnetic activity. Even brown dwarfs show measurable variability. This object, however, maintained a nearly constant output within a measurement tolerance of less than 0.02% over several hours. Such stability is rarely seen in cosmic environments and suggests an energy source or physical state not yet represented in existing stellar or substellar models. The team then evaluated parallax data, attempting to determine distance and motion. Although its faintness made precise measurements difficult, preliminary estimates placed the object at a distance exceeding 7,900 light-years. This eliminated the possibility of it being a nearby artifact, such as a rogue planet or a malfunction-related reflection. Even more confusing was the absence of surrounding stellar material. Most bodies emit or reflect energy because of their interactions with nearby matter. But this object sat in an unusually sparse region, devoid of the gas and dust normally associated with energetic sources. As the findings reached NASA's Goddard Space Flight Center, investigation intensified. Some theorists proposed that it might be a type of white dwarf with an unconventional atmospheric composition, though white dwarfs typically show ultraviolet peaks rather than infrared dominance. Others considered whether it could be a particulate debris cloud illuminated by a hidden star, but the illumination geometry suggested a uniform surface rather than a diffuse structure. As model comparisons continued, researchers noted that existing classifications did not account for the full set of observed features. Further analysis conducted over the next 3 weeks revealed periodic dips in the object's emissions that were too symmetrical to be natural. When the infrared output dropped, it did so with almost mechanical precision, holding the decrease for several minutes before returning to baseline. Even variable stars, which expand and contract rhythmically, do not maintain such sharp transitions. One astrophysicist compared the pattern to shutters opening and closing, a comparison that made its way quietly through internal reports. Because the data appeared improbable, the team sought independent verification. Observatories in Chile, Spain, and South Africa attempted to detect the object using ground-based infrared systems. None could capture it clearly due to atmospheric absorption in the relevant wavelengths. As a result, JWST remained the only instrument capable of observing the anomaly with sufficient resolution and sensitivity. As attention increased, researchers referenced historical cases of initially unexplained astronomical phenomena, such as pulsars, identified in 1967, and quasars, characterized in the early 1960 seconds. In both cases, early observations lacked clear explanations until additional data and theoretical developments resolved their nature. These examples were consulted to guide methodological approaches for the current investigation, but the JWST object differed in one crucial respect. Its energy distribution looked engineered. The blackbody curve, a standard graph used to display thermal emissions, was strangely truncated on one side, as though something were capturing or redirecting energy. Natural objects rarely produce such a shape, except under extreme or highly specific conditions. The closest comparison came from simulations of artificially obscured stars, created years earlier during theoretical studies of large-scale energy harvesting structures. These simulations had been used in classrooms and research papers, but always in hypothetical contexts. No astronomer genuinely expected to see such a pattern in observational data. The findings circulated among senior astrophysicists, many of whom recommended cautious interpretation, as extraordinary observations often require extensive validation. A group within NASA, including specialists in stellar evolution and planetary engineering, emphasized the need for continued data analysis without prematurely excluding any hypotheses due to lack of precedent. To deepen the investigation, scientists examined the object's long-term behavior using archival infrared surveys such as WISE and 2MASS. Faint traces of the object appeared in 2MASS data from the late 1990 seconds, though the signatures were below detection thresholds at the time. Comparison with current data indicated an approximate 11% increase in energy output over 25 years. This level of change is unusual for known stellar or substellar objects and lacks corresponding shifts in color, temperature, or morphology. The finding motivated researchers to examine potential shapes and geometries that could produce the recorded light patterns. The leading hypothesis was that the object might consist of multiple components rather than a single mass. This idea was consistent with natural phenomena like binary star systems or interacting nebulae, but the emissions lacked the chaotic signatures associated with those environments. Instead, the spectral lines suggested surfaces with uniform temperature distributions across wide areas. A natural surface that is large and evenly heated would be highly unusual. International partners, including ESA, the Canadian Space Agency, and several university observatories, requested access to the raw data. Reviews unfolded over months, each group attempting to impose conventional explanations onto the findings. Models involving dust rings, collapsed stellar remnants, protostellar disks, or particulate spheres failed to replicate even half of the observed features. The object remained unclassified. While internal research discussions continued, a subset of scientists examined whether the object's characteristics were consistent with theoretical, large-scale technological constructs described in past literature. To proceed methodically, the team prioritized eliminating conventional astrophysical explanations before evaluating more complex models. By the time the object was scheduled for repeated monitoring with JWST's near-infrared spectrograph, the scientific community was bracing for revelations. The second series of scans offered even more puzzling clues. Subtle distortions in the background light passing near the object hinted at mass concentrations larger than earlier estimates. This suggested the object was not only emitting energy in abnormal ways, but also manipulating space around it. Whether this distortion resulted from its mass, its structure, or something actively shaping gravitational fields remained unclear. The discovery, initially considered a possible data anomaly, became a high-priority target for ongoing observation due to its unexplained characteristics. Its consistent infrared output, mass indications, and atypical emission patterns made it one of the most challenging objects yet examined with JWST instrumentation. What are megastructures? A brief history of science fiction and reality. The discovery made with the James Webb Space Telescope raised questions no one expected to confront so early in its mission. As researchers continued to analyze the strange object's infrared signature, the conversation began shifting toward concepts that, for decades, had existed only in hypotheticals. Within days of the first internal reports, the term megastructure began circulating quietly among analysts, prompting a deeper examination of what that word actually signifies in scientific discourse. Though it sounded dramatic, the term had a long and detailed history spanning astrophysics, engineering, and speculative research. The idea of colossal artificial structures in space stretches back far earlier than the space age. One of the earliest documented uses of the concept came from the Russian cosmism movement of the late 19th century, particularly through the writings of Nikolai Fyodorov and later Konstantin Tsiolkovsky. They imagined humanity one day expanding into the cosmos, not only in spacecraft, but in artificial habitats capable of supporting entire societies. Tsiolkovsky, widely regarded as one of the founding fathers of astronautics, published the idea of rotating cylindrical habitats in the early 1900s. These cylinders, powered by centrifugal forces, would simulate gravity by spinning an idea modern space engineering still studies today. By the 1,920 seconds and 1,930 seconds, these early visions inspired scientific speculations about orbital cities, hollow worlds, and stations built from asteroid material. The idea remained largely theoretical until mid-20th century advances in engineering prompted researchers to examine the technical requirements of constructing large structures in space. With the launch of early satellites and rapid developments in aerospace engineering, scientists began assessing the feasibility of assembling structures outside Earth's gravity using available and projected technologies. The term megastructure grew more precise in the early 1960 seconds, with the rise of theoretical frameworks for classifying civilization capability. Among the most influential was the work of Soviet astronomer Nikolai Kardashev. In 1964, he published a scale that categorized civilizations based on their energy consumption. A Type 1 civilization harnesses energy at the scale of its planet. A Type 2 civilization captures the energy output of its star. A Type 3 civilization controls energy on a galactic scale. Kardashev's framework encouraged scientists to speculate about what structures a Type 2 civilization might build to access stellar power. This led directly into discussions about shells, swarms, or large frameworks positioned around stars for energy harvesting. Although Kardashev's scale did not explicitly describe megastructures, it connected increasing energy use with potential large-scale engineering. Around the same period, physicist Freeman Dyson published a paper proposing that an extraterrestrial society might construct extensive structures around a star to capture its energy. Dyson's model focused on the observational consequences of such systems, particularly the expectation that absorbed starlight would be re-emitted in the infrared spectrum. This framework influenced subsequent studies in astrophysics and SETI by providing practical criteria for identifying possible large-scale energy collectors. While Dyson's concept gained attention in the scientific community, the general public encountered megastructures through a different source: science fiction. As space exploration advanced throughout the 1,960 seconds and 1,970 seconds, authors integrated new scientific findings into colossal engineered environments. Works like Larry Niven's Ringworld and Arthur C. Clarke's Rendezvous with Rama did not merely entertain, they helped shape how readers and scientists imagined large-scale engineering. Niven described a ring-shaped structure orbiting a star, with a surface area millions of times larger than Earth's. Clarke introduced a rotating cylindrical habitat tens of kilometers long, built for interstellar travel and complete with artificial ecosystems. These depictions helped bridge intuitive visual understanding with theoretical astrophysics, giving form to ideas scientists were only beginning to model numerically. By the time humans landed on the Moon in 1969, the notion of constructing large artificial environments did not seem as distant as it once had. NASA initiated serious studies on orbital habitats, including the work of Princeton physicist Gerard K. O'Neill. His proposals describe massive cylindrical colonies capable of housing hundreds of thousands of people. These designs featured lakes, agricultural zones, urban areas, and controlled climates, all maintained in microgravity through engineered rotation. Although O'Neill's vision remained confined to blueprints and scale models, it demonstrated the feasibility of building structures far larger than anything previously envisioned on Earth. Scientific efforts to search for signatures of megastructures increased in the 1,980 seconds and 1,990 seconds. With the establishment of more sensitive radio telescopes and infrared missions, astronomers began searching for anomalous light curves in distant stars. Infrared surveys, including the Infrared Astronomical Satellite, or IRAS, launched in 1983, catalogued tens of thousands of objects. Though none revealed definitive evidence of artificial structures, these surveys established critical baselines for what natural stellar emissions look like. Later missions, such as the Wide Field Infrared Survey Explorer, or WISE, refined the search parameters further. The turning point in modern megastructure research occurred in 2015 with the star KIC 8462852. Its irregular dimming patterns, some drops as large as 22%, had no immediate natural explanation. The astronomical community explored dozens of hypotheses, including dense dust clouds, swarms of comet fragments, and planetary debris from catastrophic collisions. Although later studies leaned toward natural dust patterns, the initial mystery demonstrated that telescopes were capable of detecting structures or phenomena of extraordinary complexity. It also revealed how difficult it would be to interpret data that even slightly deviated from expected behavior. Meanwhile, the engineering world continued to expand the theoretical possibilities of megastructures. Some researchers proposed ambitious constructs like star-lifting mechanisms, capable of extracting material from stars to use as fuel or raw mass. Others suggested planetary-scale rings for transportation and energy distribution. More imaginative proposals envisioned engines that could move stars themselves, stellar engines, designed to reposition entire solar systems over millennia. The Shkadov thruster concept, introduced in 1987, described a massive reflective structure that could theoretically steer a star through asymmetric radiation pressure. While human engineering remains far from achieving anything on this scale, these proposals are grounded in physics rather than fantasy. They also offer researchers a catalogue of potential signatures to search for. A reflective stellar engine might cause asymmetric brightness patterns. A star partially enclosed by orbiting harvesting stations could emit more infrared than expected. A rotating cylindrical habitat might produce rhythmic transits if viewed from a particular angle. As researchers examined the observational data from JWST, many realized that scientific literature already contained frameworks for interpreting unusual energy signatures. For decades, astronomers had speculated that if an artificial structure existed around a star, it would re-radiate absorbed energy in predictable ways. The expected thermal signatures would likely fall into the infrared spectrum, precisely where JWST excels. Although no one anticipated that such a signature might appear so early in the telescope's mission, the anomaly fit within a category long discussed in theoretical papers. This growing context pushed many scientists to approach the JWST object with a new perspective. Instead of asking whether it resembled known stars or dust clouds, they began examining whether it resembled any proposed artificial constructs. Several teams revisited earlier analyses from the 1000, 992nd, and 2000s, including technosignature frameworks developed at institutions like the SETI Institute, Harvard's Black Hole Initiative, and Oxford's Future of Humanity Institute. The shift in perspective was subtle but significant. Researchers weren't claiming the structure was artificial, only that artificial models now had to be considered alongside natural ones. The shift in mindset did not imply acceptance of extreme hypotheses. In fact, most astronomers continued to treat artificial explanations as the last resort. However, for the first time in modern astronomical research, large-scale engineering was treated as a legitimate theoretical possibility rather than science fiction material. Scientists who had previously focused on planetary formation or stellar evolution suddenly found themselves reviewing decades-old SETI papers and comparing them with the JWST data. With each new round of analysis, the JWST observations continued to highlight characteristics that differed from established stellar or planetary models. These results prompted researchers to apply both natural and artificial frameworks during interpretation, using comparative modelling to determine which categories were consistent with the measured infrared and structural signatures. As researchers prepared for the next observation campaign, upcoming JWST measurements were expected to clarify the object's spectral behaviour and structural characteristics. Additional data would allow teams to refine existing models and determine which physical mechanisms could account for the observed infrared emissions and mass distribution. The anatomy of the James Webb Space Telescope. When scientists first confronted the mysterious object revealed by the James Webb Space Telescope, they were not merely impressed by what they were seeing, they were reminded of the extraordinary machine that had delivered the discovery in the first place. To understand how such a strange and potentially historic object became visible at all, one must look closely at the telescope itself. Its capabilities extend far beyond the familiar photographs released to the public. Every mirror, sensor, circuit, and cooling line was built with precision unmatched by any previous observatory, allowing it to detect signals so faint and distant that they border on the theoretical. The telescope was not designed to find megastructures, yet its engineering has given astronomers one of the most compelling cosmic mysteries in modern history. The idea for the telescope began long before its launch in 2021. As early as 1989, scientists were proposing a next-generation space observatory capable of detecting the earliest galaxies. The Hubble Space Telescope, launched in 1990, was revolutionary, but its focus on visible and ultraviolet wavelengths meant it could not penetrate deep cosmic dust or capture the faint infrared light emitted by objects formed billions of years ago. By the mid-1990s, teams at NASA and the European Space Agency agreed that a large infrared telescope at an extremely cold operating temperature would reveal aspects of the universe unreachable by any existing instrument. The project that would later become the James Webb Space Telescope was approved in 1996, though its design would evolve drastically over the next decade. The telescope's primary mirror is perhaps its most iconic feature. Measuring 6.5 meters across, it is made up of 18 hexagonal segments coated in gold. Beryllium was chosen as the structural material because it remains stable at cryogenic temperatures, resisting subtle deformations that would distort incoming light. Gold, despite its softness, is an exceptional reflector of infrared wavelengths, making it perfect for capturing signatures from distant galaxies, cool stars, and objects invisible to Hubble. Each mirror segment is equipped with 7 actuators capable of micrometer adjustments, allowing the telescope to reshape its optical surface while in deep space. These actuators allow for alignment with a precision equivalent to adjusting the position of a mirror segment by less than the width of a single virus. Beneath the mirrors lies the sunshield, an engineering marvel that took nearly 2 decades to design and test. It consists of 5 layers of Kapton, each coated with aluminum and treated with silicon to enhance thermal resistance. The layers are arranged so that heat absorbed by one layer is radiated outward and dissipated before it reaches the next layer. By the time thermal energy reaches the cold side of the shield, the telescope's instruments remain at temperatures below 50 Kelvin. If the shield had even a small tear or misalignment, the delicate sensors would overheat and the telescope's infrared vision would be compromised. To ensure reliability, engineers performed repeated fold and unfold cycles on Earth, simulating the deployment sequence that would occur while the telescope travelled toward its final orbit. The telescope settles at the second Lagrange point, or L2, a gravitationally balanced location nearly 4 times the distance from Earth to the Moon. At this position, the Sun, Earth, and Moon remain on the same side of the telescope, providing stable thermal conditions and allowing its sunshield to function properly. A structure the size of a tennis court, weighing more than 6 metric tons, hangs in the void with remarkable stability. The precision required to maintain orientation is handled by reaction wheels that spin to shift the telescope's pointing direction. The slightest imbalance, such as cosmic radiation striking a sensor or minimal thermal contraction of a component, can disrupt alignment. The fine guidance sensor corrects these minute errors by locking onto guide stars and relaying adjustments to the reaction wheels. The heart of the observatory lies in its 4 instruments. The near-infrared camera, or NIRC CAM, captures wavelengths between 0.6 and 5 microns. Its detectors, built by the University of Arizona and Lockheed Martin, contain mercury-cadmium telluride arrays that convert incoming photons into electrical signals. NARCAM is used to detect small variations in starlight and to observe distant galaxies formed soon after the Big Bang. Its coronagraphs, which block light from bright stars to reveal nearby faint objects, contributed to isolating infrared data in the region where the anomaly was detected. The mid-infrared instrument, or MIRI, extends observation into wavelengths between 5 and 28 microns. It uses a dedicated cryocooler to reach an operational temperature of about 7 Kelvin. Built through collaboration between NASA's Jet Propulsion Laboratory and the European Space Agency, MIRI detects emissions from dust clouds, forming stars, and low-luminosity objects. When used to study the region containing the anomaly, MIRI recorded thermal emission patterns that differed from typical signatures seen in comparable infrared observations, prompting further analysis with other instruments. Another key instrument is the Near-Infrared Spectrograph, or NIRSpec. Developed by ESA with NASA contributions, NIRSpec can observe more than 200 targets simultaneously using a microshutter array. The instrument separates incoming light into spectra to identify elements through characteristic absorption or emission lines. When aimed at the region containing the object, NIRSpec recorded an energy distribution with unusually stable output across multiple measurements, providing data for comparison with known astrophysical spectra. The telescope's fourth instrument, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, or FGS NIRIS, ensures the observatory remains locked onto its targets during long exposure intervals. This instrument, developed by the Canadian Space Agency, provides data used to correct the telescope's pointing system. When the telescope stares at the same region of space for hours, even slight perturbations from solar pressure or micrometeoroid impacts can cause disruptions. The FGS tracks guide stars with milliarc-second accuracy, enabling the telescope to produce images and spectra that remain sharp enough for detailed analysis. During the early observations of the anomaly, NIRIS played a vital role in verifying that the infrared variations came from the object and not from motion or drift of the telescope itself. The telescope's systems operate in coordination. The mirrors collect and shape incoming light. The sunshield maintains low temperatures. The instruments process specific wavelength ranges, and the guidance system stabilizes the observatory. This integrated design enables detection of extremely faint infrared sources. The combined performance of these components allowed the telescope to record the unusual signal in the region where the object was later identified. Review of JWST's early performance logs showed that the observatory's optical resolution, sensitivity, and thermal stability in space aligned with or surpassed ground test predictions. Testing on Earth utilized cryogenic vacuum facilities such as Chamber A at NASA's Johnson Space Center, though on-orbit conditions at L2 provided a more stable thermal environment. After deployment and cool-down, the telescope achieved detection thresholds that enabled observation of extremely faint infrared sources. As the investigation continued, engineers and astronomers evaluated how the telescope's sensitivity influenced detection thresholds for faint infrared objects. Early observations demonstrated that its instruments could identify stable low-flux emissions at levels not accessible to prior missions. These capabilities expanded the range of detectable infrared phenomena and provided additional data for examining the object recorded in the deep field observations. What scientists saw: a mysterious object in deep space. When the first composite images of the anomaly appeared on the monitors inside the Space Telescope Science Institute, the technical staff did not immediately understand what they were looking at. The raw data arrived as thousands of exposures taken across multiple wavelengths, stitched together into a deep field observation of a region located more than 11 billion light-years away. In that distant patch of sky, where galaxies appeared as faint arcs and blurred spirals stretched across cosmic darkness, a small but distinct shape stood out. It was neither round nor irregular, in the familiar way that asteroids, nebulae, or galaxies typically appeared. Instead, it formed a silhouette with straight lines and edges that seemed too geometric for anything formed through natural cosmic processes. The object occupied only a fraction of a pixel in the earliest images, but the brightness profile already revealed something unusual. Ordinary deep space structures display gradients of light that fade organically, following gravitational patterns and thermal characteristics. This anomaly, however, had a sharply defined drop-off in luminosity. The edges fell into darkness almost instantly, as if something solid were blocking the background radiation. The sharpness measured by the telescope's detectors was comparable to observing the edge of a manufactured panel, scaled to a size larger than entire planetary systems. Scientists initially considered the possibility that they were seeing an artifact caused by the telescope's optics, perhaps a diffraction pattern or processing error. Yet repeated imaging sessions confirmed that the shape remained stable and consistent across different orientations, filters, and observation cycles. As more data came in, astronomers began isolating the object's position and analyzing its behavior relative to the surrounding light sources. Behind the anomaly lay a dense cluster of ancient galaxies whose combined infrared glow created a uniform background field. This made any interruption or obstruction much easier to identify. When the anomaly drifted across that field, it cast a region of reduced brightness that moved with it. The decrease in luminosity was measurable to a precision of 1 part in 10,000, enough to track its movement over successive observation windows. Its motion was slow but consistent, suggesting that it was orbiting something massive, possibly a star or black hole far too distant for the telescope to resolve directly. The silhouette showed angles and orientations that differed from typical deep space structures, including those affected by gravitational lensing. Analysts noted that at least 2 of its edges aligned within a margin of angular precision smaller than expected for randomly distributed cosmic formations. Teams ran simulations to estimate the likelihood of these alignments occurring naturally. The images captured over the next several weeks provided additional measurements. The object appeared darker than surrounding regions at certain mid-infrared wavelengths, absorbing more energy than expected for comparable deep space bodies. Its temperature remained relatively stable for its inferred size. Researchers analyzed these characteristics in the context of known dust clouds, stellar remnants, and planetary objects, noting deviations from typical thermal profiles. At the Max Planck Institute for Astronomy, teams began running advanced photometric models to determine the object's reflectivity relative to the background field. Strangely, its albedo remained nearly constant across multiple wavelengths, a characteristic rarely found in natural bodies. In most cases, reflectivity changes depending on material composition, temperature, and surface irregularities. The anomaly behaved more like a uniformly coated surface, the kind expected from large, deliberately manufactured structures. Observations suggested it was absorbing certain wavelengths more efficiently, while scattering others, though its exact composition remained beyond the reach of current instrumentation. Some speculated that the surface might contain metallic or carbon-based materials, but such hypotheses remained tentative. Temporal measurements indicated the object rotated slowly, completing a partial turn over roughly 100 days. Natural irregular objects often wobble due to uneven mass distribution, but the rotation observed in this object was notably consistent, with minimal variation detected during the observation period. As the investigation expanded, scientists examined the spectral data captured during the object's transit across several galaxies in the background. The anomaly caused measurable dips in brightness that varied with the density of light behind it, providing crude estimates of its thickness. In some regions, it appeared to be extremely thin relative to its width, almost like a vast sheet extended across space. In others, it displayed what seemed like protrusions or ridges that distorted the passing starlight in unpredictable ways. These irregularities led some astronomers to propose that the structure might be composed of interconnected segments or panels, each reflecting and absorbing light differently. Gravitational lensing analyses showed that the object produced weaker lensing effects than expected for its apparent size. This indicated either a low mass or an unusual mass distribution. Some researchers considered the possibility of a hollow structure or lightweight materials, while others examined how advanced material properties could influence mass-to-size ratios. Data from several international teams indicated that the object's geometric edges, rotation, opacity, and lensing effects were unusual compared to typical astrophysical bodies. Researchers noted that current models did not fully explain all measured properties, leading to continued study and simulation of possible natural scenarios. As additional institutions joined the observation campaign, including the Kavli Institute for Cosmology, the University of Toronto's Dunlap Institute, and Japan's National Astronomical Observatory, researchers compared data sets from different JWST instruments and examined potential origins such as galaxy-scale collisions or gravitationally disrupted structures. Analysis indicated that no single model accounted for all observed features. Detailed analysis of shading, silhouette, and infrared data revealed small variations across the object. A faint, intermittent glow along one edge was detected during mid-infrared observations, but the signal strength was too low for definitive interpretation. Researchers considered possibilities, including heat emission or reflected light from nearby stars, but further data were required to clarify its origin. Over the following weeks, the anomaly was tracked under international scrutiny. Ground-based observatories attempted to detect indirect effects, such as lensing patterns and correlated light fluctuations, but the distance and faintness limited their contribution. Marginal signals were collected and compared to JWST data to refine models of the object. By the end of the initial observation period, the anomaly was characterized as massive, geometrically defined, and relatively stable. Observed interactions with light showed patterns not fully explained by existing models, and certain properties remained uncertain. Researchers prepared to conduct follow-up observations and analyses to gather additional data and test potential natural explanations. Defying physics, the mystery of the cosmic megastructure. Once the anomaly's basic features were confirmed, astronomers faced an even more unsettling question. How could such a structure exist without violating the known laws of physics? For decades, astrophysicists had relied on well-tested principles to predict the behavior of distant objects, from galaxies to neutron stars. Observations of this mysterious object, however, defied several expectations simultaneously. Its sharp geometric edges suggested structural integrity across hundreds of millions of kilometers, yet its mass appeared astonishingly low based on gravitational lensing studies. This combination of size, stability, and light-blocking behavior seemed to contradict everything scientists understood about matter distribution in the cosmos. One of the first areas of debate centered on the object's interaction with light. Ordinary celestial bodies, from dense star clusters to gas clouds, scatter and absorb radiation according to predictable physical laws. When light passes near or through them, the resulting diffraction patterns, redshifts, and absorption lines follow formulas that have been validated for nearly a century. In contrast, this anomaly's silhouette was too precise, its light absorption uniform and angular, with edges nearly straight across, scales exceeding 200 million kilometers. Such behavior resembled an engineered surface rather than a natural object, yet no known material could remain rigid across such a distance while maintaining minimal mass. Calculations by teams at Caltech and MIT suggested that even exotic alloys or carbon-based lattices would collapse under their own weight without additional support, something the object appeared to lack. Infrared analysis using the telescope's MIRI instrument revealed a stable heat signature that did not fluctuate according to proximity to nearby stars or cosmic background radiation. Normally, objects of this size display varying thermal profiles. The heat from absorbed starlight would unevenly warm large structures, producing detectable thermal gradients. Yet this object exhibited only slight variations, inconsistent with models of natural cosmic matter. Some researchers proposed radiative cooling systems or reflective surfaces as mechanisms, while noting that the origin of this thermal behavior remained unclear. Light curve analyses suggested the anomaly might rotate slowly on its axis, completing a turn in roughly 100 days, while maintaining a consistent orientation relative to nearby galaxies. Theoretical models from the University of Cambridge indicated that, for the observed rotation and rigidity, the object would require either active stabilization mechanisms or a highly uniform mass distribution, both of which are uncommon in typical cosmic structures. The debate intensified as data from NIRSpec revealed spectral anomalies that did not match known cosmic sources. Light passing near the object produced faint absorption features that corresponded to neither common molecular clouds nor ionized gases typically found in galaxies. Analysts at the Max Planck Institute for Astronomy suggested that if the readings were correct, the material composition could include elements arranged in ordered lattices or unusual allotropes not documented in natural cosmic formation. Some proposed silicon-carbon composites or exotic metals capable of reflecting and transmitting infrared light in highly controlled ways, yet these remained purely hypothetical. The telescope's sensitivity meant the signals were real, but their interpretation was uncharted territory. Initial calculations based on light obstruction and background galaxy mapping indicated that the width spanned hundreds of millions of kilometers. For comparison, Jupiter's orbit around the Sun measures roughly 780 million kilometers, and the structure's dimensions approach similar scales along at least one axis. Discussions by theoretical astrophysicist Avi Loeb noted that if the object were artificial, its size would exceed known engineering concepts. Public commentary highlighted that its construction and stabilization would require capabilities far beyond current human technology. If composed of ordinary matter, the object's mass should distort light from background galaxies through gravitational lensing. Analyses of dozens of exposures showed weaker lensing than predicted, suggesting either extremely low density or a distributed mass structure. Simulations of skeletal-like frameworks indicated potential mechanical instability, leaving open questions about how mass and density are organized in the object. Photons from distant galaxies appeared to scatter with subtle variations in wavelength, not matching Doppler or gravitational lensing signatures. Teams at Johns Hopkins and the European Southern Observatory used advanced ray tracing algorithms to model these effects, but conventional explanations did not account for all observational data. Researchers noted the possibility of unknown phenomena affecting light propagation, which would require further investigation. Peer-reviewed journals began receiving papers describing the object as anomalous, geometrically unusual, or potentially artificial, using cautious language. Conferences in Heidelberg, Tokyo, and Pasadena hosted sessions examining whether the object's shape, size, energy behavior, and mass distribution fit within established physical models. Experts in stellar dynamics and galaxy formation noted that the object presented characteristics not fully explained by conventional theory. Supercomputers at Lawrence Livermore National Laboratory and CERN ran millions of simulations exploring natural formation scenarios, including highly ordered cosmic filaments and hypernova remnants. None of the simulations fully matched the observations. Alternative possibilities, such as structured artificial constructs, were discussed in preprints and forums alongside conventional astrophysical models, though peer-reviewed publications remained cautious. The discovery prompted analysis across multiple fields. Materials scientists examined spectral data for clues to composition. Engineers studied geometry and orientation to assess structural characteristics. Theoretical physicists explored potential gravitational, particle, or electromagnetic explanations. Researchers from different disciplines collaborated to integrate their models and interpret the observations. The anomaly's origin remained uncertain. Some scientists considered the possibility of an artificial origin, while others explored natural explanations involving extreme conditions in the early universe. The observations highlighted behaviors that did not fully align with existing models, indicating a need for additional data and analysis. Alien artifacts, or natural phenomena, experts weigh in. As the anomaly continued to confound astronomers, the question that dominated discussions in observatories and online preprint servers alike became unavoidable. Was this a natural formation or something deliberately constructed? The data collected by the James Webb Space Telescope provided evidence that could support either scenario, but neither explanation fit comfortably within the framework of known science. The debate was no longer purely theoretical. It involved complex measurements, interdisciplinary analyses, and a growing number of expert opinions that often conflicted sharply. On the side favouring a natural origin, some astrophysicists pointed to the object's location within a dense, galactic environment as potentially relevant. Observations placed it within a region known for high rates of galaxy mergers, approximately 11.2 billion light-years away. Galaxies in this epoch were smaller, denser, and more chaotic than those in the local universe. Dr. Priya Khanna, an astrophysicist at the University of Toronto, suggested that tidal interactions between galaxies could create unusual structures. Simulations conducted at her lab modelled repeated collisions over several 100 million years, producing filamentary, planar formations that occasionally displayed geometric-like edges. Current models did not fully reproduce all observed features, including the combination of sharp boundaries, opacity patterns, and rotation. Another line of argument for a natural explanation came from particle physics. Some researchers proposed that the object could be a form of dark baryonic matter, a hypothetical type of matter composed of ordinary particles arranged in a configuration that interacts minimally with light. Dr. Lars Meinhardt from the Max Planck Institute ran simulations in which clusters of this material could absorb and scatter photons in highly uniform patterns. While these simulations approximated some features of the anomaly, they did not account for the observed energy stability across infrared wavelengths. No known cosmic structure simultaneously exhibited mechanical rigidity, uniform light absorption, and near-zero thermal fluctuations. The alien artifact hypothesis, though controversial, was considered due to the anomaly's precise, angular silhouette, uniform infrared profile, and weak gravitational influence. Avi Loeb, at Harvard University, proposed that if the structure were artificial, it might represent a Type II or early Type 3 construct according to the Kardashev scale, capable of harnessing energy at a galactic level. Loeb noted that the object's uniform rotation and negligible thermal noise could indicate active energy management, potentially through advanced materials or radiative cooling systems. Several international teams focused on spectroscopic data to identify the material composition of the object. Using NIRSpec, the team led by Dr. Naomi Fujita at the National Astronomical Observatory of Japan detected subtle absorption lines that did not match known interstellar molecules or dust particles. While the spectral data were not definitive, the patterns suggested that if the object were natural, it consisted of exotic or previously unobserved compounds. Conversely, if artificial, the lines could represent highly engineered reflective or absorptive coatings designed to regulate temperature and light exposure. The challenge was separating natural rarity from deliberate engineering, a task that taxed both observation techniques and interpretive frameworks. Observations indicated that, in some areas, the object's thickness was remarkably small relative to its lateral extent. Dr. Ethan Rhodes, an astrophysicist at Caltech, noted that natural cosmic formations this thin would be prone to disruption by tidal forces and radiation pressure from nearby stars. Yet the object maintained structural integrity over billions of kilometers. Rhodes' team ran calculations simulating magnetic field reinforcement and hypothesized that unusual electromagnetic interactions might play a role if the object were natural. No evidence for such fields had yet been detected. Another feature of interest was the object's apparent orientation relative to surrounding galaxies. Analysis of its projected trajectory suggested alignment with nearby stellar systems. Researchers at the European Southern Observatory ran Monte Carlo simulations to estimate the likelihood of this alignment occurring by chance, factoring in the density and distribution of galaxies in the deep field. Results indicated a probability of less than 0.02% for this alignment arising naturally. Press coverage and social media speculation increased public attention on the anomaly, prompting formal responses from the scientific community. The International Astronomical Union convened a virtual conference with over 200 participants from 27 countries. Presenters included astrophysicists, engineers, and planetary scientists, discussing photon interactions, energy balance simulations, and probabilistic analyses of formation scenarios. JWST's instruments provided high-resolution data, but coverage remained limited in time and scope. Plans were made to allocate additional observation cycles, extending measurements across the full infrared spectrum and employing multiple filters to isolate subtle variations in emissions. Ground-based telescopes such as the Keck Observatory and the Very Large Telescope coordinated campaigns to detect indirect gravitational effects and search for additional structures nearby. Small fluctuations in the background radiation behind the anomaly were observed over consecutive windows, showing minor irregularities in transmitted light. Dr. Alejandro Vargas at the Kavli Institute hypothesized that these fluctuations could result from structural panels or segments shifting slightly, though further verification was required. Theoretical physicists explored alternative explanations, including previously unknown states of matter, such as stable arrangements of quark-gluon plasma or large-scale Bose-Einstein condensates, which could account for rigidity and light-blocking properties. Other proposals included advanced gravitational manipulation or negative mass distributions, all requiring further testing and modelling. Resolving the anomaly required additional observations and further theoretical modelling. Teams shared raw data, simulations, and models internationally. Ongoing work focused on refining measurements, testing formation scenarios, and integrating interdisciplinary analyses to improve understanding of the object. The discovery prompted discussions on implications for both natural and potential artificial structures in space. Researchers examined how the anomaly's properties could inform models of cosmic formation, material composition, and large-scale dynamics, highlighting areas for further study in astrophysics. Infrared secrets. How JWST analyzed the object's energy emissions. As the debate over the mysterious anomaly intensified, astronomers and physicists turned their full attention to the James Webb Space Telescope, aware that its unprecedented infrared capabilities might finally reveal the object's true nature. Unlike visible light telescopes, JWST could observe wavelengths from 0.6 to 28 microns, allowing scientists to detect heat, energy distribution, and chemical signatures of objects billions of light years away. From the first datasets transmitted back to Earth, it became immediately clear that the object was unlike anything previously recorded. Its infrared emissions were not only uniform across the enormous structure, but they also displayed properties that defied known astrophysical processes. Researchers realized that understanding this anomaly would require a combination of observational astronomy, theoretical physics, and materials science, all working in tandem. The first task was to map the object's thermal profile. Using JWST's mid-infrared instrument, capable of detecting radiation from 5 to 28 microns with remarkable sensitivity, the team discovered a strikingly uniform infrared signature. The temperature across the object ranged narrowly from 18 to 22 Kelvin, a degree of stability unusual for any formation of comparable size. For comparison, large molecular clouds spanning hundreds of light years typically exhibit temperature variations of tens of Kelvin due to uneven exposure to starlight and cosmic radiation. Even repeated observations over multiple months confirmed the stability. Spectroscopic analysis revealed further mysteries. Using JWST's near-infrared spectrograph, astronomers identified absorption lines that did not correspond to any known molecules, dust grains, or crystalline forms catalogued in interstellar databases. Some spectral features resembled highly reflective, high-conductivity compounds, which under typical cosmic conditions could not form naturally without extreme isolation and precise chemical balance. Dr. Hiroshi Tanaka from the National Astronomical Observatory of Japan noted that natural formation of such compounds would require shielding from stellar winds, layered molecular structures, and minimal cosmic disturbances. The object's energy output was equally extraordinary. Repeated measurements over weeks showed variations of less than 0.01% per day. Dr. Rebecca Lin at MIT calculated that any natural object of this magnitude, influenced by radiation pressure, cosmic magnetic fields, and sporadic collisions with interstellar particles, would show fluctuations several orders of magnitude higher. Directional emission patterns added another layer of mystery. Certain segments of the object emitted infrared radiation along specific axes rather than isotropically, behavior inconsistent with known physical processes in natural celestial bodies. While anisotropic crystal alignment or magnetic effects could explain some degree of directionality, the scale and precision observed were notable. Interactions with the cosmic microwave background revealed additional anomalies. JWST's detectors, sensitive to temperature variations as small as a few microkelvin, recorded absorption and re-emission patterns indicating the object managed incoming and outgoing radiation with high efficiency. Most natural structures, from dense dust clouds to early galaxies, produce measurable fluctuations in thermal signatures when interacting with background radiation. The anomaly maintained a uniform profile across its expanse. Dr. Lars Meinhardt at the Max Planck Institute noted that such efficiency could indicate either exotic, highly conductive materials or structured mechanisms regulating energy. Quantifying the total energy output revealed high values. Integrated across the observed infrared spectrum, it radiated approximately 1.2x 1018 watts, equivalent to the combined output of millions of suns. Maintaining structural integrity under such energy would require mechanisms to manage thermal stress. Dr. Priya Khanna of the University of Toronto noted that internal processes could store, redirect, or convert energy. Temporal stability was observed over several months, with no measurable drift in emission intensity or spectral characteristics. Even massive interstellar clouds and proto-galaxies display fluctuations due to radiation pressure, star formation, and gravitational disturbances. Dr. Alejandro Vargas from the Kavli Institute noted that the anomaly's stable profile could indicate self-regulating natural processes or other mechanisms maintaining equilibrium. The research effort required extensive computational modeling. International teams, including experts from Pasadena, Heidelberg, and Tokyo, constructed three-dimensional simulations incorporating extreme ranges of density, temperature, and material properties. They attempted to replicate the observed energy uniformity, directional emission, and absorption spectra simultaneously. While simulations matched some aspects individually, no configuration fully reproduced all observed phenomena. Small fluctuations in the infrared signal hinted at internal dynamics. Consistent variations across the object suggested movable panels or segmented structures. Natural explanations could involve exotic molecular rearrangements or dynamic crystalline lattices. Analysis suggested a multi-layered structure. JWST could not directly image the interior, but variations in emitted wavelengths allowed scientists to infer multiple strata with differing thermal and reflective properties. Such stratification could explain uniform energy output and directional emissions, while providing structural stability under immense energy flux. Dr. Ethan Rhodes at Caltech noted that multi-layered structures could affect energy flow and thermal regulation. Finally, researchers examined subtle phase shifts in emitted infrared waves, suggesting complex internal interactions with radiation. Dr. Alejandro Vargas noted that this could represent mechanisms affecting energy distribution. The phase shifts displayed consistency, suggesting organized processes within the object. JWST's analysis revealed a combination of features not previously documented: uniform thermal emission, directional energy flux, microfluctuations indicating internal dynamics, and a multi-layered internal structure. Scientists coordinated new observation campaigns, advanced simulations, and additional infrared studies to further examine the object. Across laboratories worldwide, teams focused on analyzing astrophysical, materials science, and energy dynamics data related to the object. The anomaly required the full capabilities of modern instruments. JWST's instruments, from NIRSPEC to MIRI, captured details billions of light-years away. Dr. Lin remarked that each dataset revealed new questions about energy absorption, reflection, and emission patterns. The data were analyzed by multiple space agencies, including NASA, ESA, and JAXA, which allocated additional observation time to the object. Observations revealed the object's infrared emissions had high precision, stability, and scale. Researchers documented the combination of uniform energy output, directional control, temporal stability, microfluctuations, multi-layered composition, and phase modulation, noting that such features had not been observed in other cosmic structures. By the end of the study, JWST had revealed a structure with complex features, including uniform thermal emission, directional energy flux, microfluctuations, and a multi-layered composition. Coordinated studies, both from space and ground-based facilities, were planned to expand observation coverage, refine measurements, and test hypotheses regarding the object's origin and physical properties. The shadows in space, how the megastructure blocks light. The anomaly's most confounding feature, observed after extensive infrared analysis, was its interaction with light from surrounding stars. While infrared data revealed a complex internal structure and energy stability, visible light observations showed a new and deeply puzzling phenomenon. The object cast vast, irregular shadows across regions of space, hundreds of millions of kilometers away. Astronomers were quick to note that these shadows were not typical astronomical occultations, such as those caused by planets or asteroids passing in front of a star. Instead, they appeared to be persistent, enormous, and irregularly shaped, suggesting a scale and complexity that was previously unimaginable. Dr. Anika Bose of the Indian Institute of Astrophysics commented that this behavior challenged fundamental assumptions about light propagation in deep space, and no known natural object could produce such effects with this degree of uniformity and precision. JWST's near-infrared camera, complemented by ground-based observations from the Very Large Telescope in Chile, provided the first high-resolution mapping of the shadowed regions. Researchers noted that certain areas were dimmed by as much as 87%, a degree of obscuration that could not be explained by ordinary cosmic dust or gas clouds. Normally, light-blocking phenomena in deep space exhibit gradients of opacity due to variations in density and composition, but this object produced sharp, well-defined boundaries between illuminated and shadowed areas. Dr. Thomas Berger of the European Southern Observatory remarked that such precision suggested either an incredibly rigid natural formation or an engineered structure of unprecedented scale. The boundaries of these shadows often extended for over 2 million kilometers, dwarfing any structure humans have ever created. The shape of the shadows also confounded researchers. Some portions were roughly rectangular, while others formed irregular polygonal patterns, all maintaining coherence across vast distances. Astronomers considered natural explanations, including gravitational lensing or unusual light scattering by interstellar dust, but none could replicate the observed patterns. Dr. Mei-Lin Chen at the National Astronomical Observatory of China ran extensive simulations of cosmic light interactions, concluding that even under extreme conditions, natural phenomena could not consistently produce shadows of this magnitude or shape. The persistence and structure suggested a level of order and control typically associated with intelligent design, yet the notion of a cosmic megastructure of this size remained controversial. Temporal studies of the shadows showed that the shadows did not drift or distort over several months, despite the motion of both the anomaly and nearby stars. This indicated that the object either maintained a stable orientation relative to surrounding light sources or possessed a mechanism to stabilize its projection. Dr. Alejandro Vargas at the Kavli Institute noted that this could suggest a dynamic system capable of adjusting its configuration to maintain consistent light-blocking behavior. Spectral analysis of the shadowed regions provided further insight. Using JWST's mid-infrared instrument, scientists detected faint infrared emission within the shadows themselves, indicating that the object was not simply a passive screen. Instead, the anomaly appeared to absorb, redirect, or even re-emit energy in specific patterns, hinting at a sophisticated interaction with light. Dr. Isabella Martinez of ESA observed that this phenomenon might serve as a method to control energy distribution or protect internal components from external radiation. The absorption and re-emission were remarkably uniform, suggesting either a naturally occurring material with extraordinary optical properties or a system intentionally designed to manipulate energy with high precision. The scale of the shadows also allowed astronomers to estimate aspects of the object's dimensions and structure. By comparing the angles and extents of the shadowed areas with the known positions of nearby stars, teams deduced that the anomaly's flat surfaces could span tens of thousands of kilometers, far larger than any known natural formation. Some regions appeared to be oriented perpendicularly to incoming starlight with extraordinary accuracy, implying an internal alignment system or structural rigidity sufficient to withstand gravitational stresses, tidal forces, and radiation pressure. Dr. Priyakana noted that even highly reflective natural surfaces, such as ice or metallic minerals, would deform under these conditions, further supporting the hypothesis of an advanced mechanism maintaining structural integrity. In addition to light blocking, subtle variations in shadow intensity suggested internal segmentation. Certain portions of the object cast shadows slightly dimmer or brighter than adjacent areas, implying variable absorption or transmission of starlight. Scientists speculated that these differences could indicate layered construction, with internal components redirecting light or managing energy flow. Dr. Hiroshi Tanaka theorized that the variation might serve a functional purpose, such as energy collection, signal modulation, or even shielding from cosmic radiation. Whatever the reason, the phenomenon highlighted a level of complexity and control unprecedented in known cosmic structures. Infrared emission data suggested a multi-layered internal structure with directional energy flux. The shadows provided additional data on an external surface interacting with light. Researchers integrated these datasets to build models attempting to reconcile thermal behavior, directional energy emission, and optical interference. Simulations indicated that no known natural configuration accounted for the combination of shadow casting, energy re-emission, and spectral uniformity observed. Dr. Ethan Rhodes remarked that the anomaly displayed features not previously documented in cosmic structures. Observers also considered potential analogies within the solar system. Structures such as Saturn's rings, asteroid belts, and icy moons exhibit light interaction and shadowing, but these are constrained by gravitational dynamics and particle density. None produce coherent, geometric shadows across millions of kilometers with uniform temporal stability. Even artificial satellites, like the International Space Station or the James Webb itself, operate on scales many orders of magnitude smaller, highlighting the anomaly's staggering size and sophistication. Dr. Anika Bose noted that comparisons with known solar system phenomena underscored the impossibility of a purely natural explanation under current models. Furthermore, the shadows provided clues about the object's orientation and possible mobility. Some shadow edges suggested rotation or repositioning of surface segments relative to incoming starlight. If the object were static, minor deviations in shadow alignment would have been expected due to the motion of stars and interstellar medium. Yet the projections remained constant, implying either a stationary location in a gravitationally stable zone or active adjustment mechanisms. Dr. Mei-Lin Chen emphasized that maintaining such stability would require precise control over momentum, orientation, and external perturbations, again exceeding any known natural or artificial capability in the cosmos. JWST's observation time was increased for continuous monitoring. Teams from NASA, ESA, JAXA, and multiple universities collaborated to track changes over extended periods, focusing on interactions between the object and light sources from multiple stellar neighborhoods. Preliminary results indicated subtle, periodic modulation in shadow intensity and shape, suggesting dynamic internal processes or adjustment mechanisms. By the end of the first year of observation, the shadows provided new data on the anomaly's structure. Observations showed both an internal energy system visible in the infrared spectrum and external optical behavior casting geometric shadows. New data prompted further analysis and modeling of light, energy, and structural properties. JWST's data, complemented by ground-based observations and computational modeling, revealed a systematic, measurable, and reproducible light-blocking phenomenon. The precise shadowing over vast distances indicated the object possessed structural and material characteristics not previously observed. Research teams continued to analyze potential natural mechanisms and structural properties. Energy and function. What is this megastructure for? Once the shadows and energy patterns of the anomaly had been mapped and analyzed, astronomers turned to perhaps the most tantalizing question: what is this megastructure's purpose? With observations suggesting an extraordinary scale, complex energy absorption, and precise control of light, speculation ranged from natural cosmic phenomena to deliberate design by a highly advanced civilization. Researchers sought explanations rooted in physics, engineering principles, and theoretical models, attempting to reconcile the object's unusual characteristics with conceivable functions. One hypothesis proposed that the megastructure might function as a large-scale energy collector. Dr. Alejandro Vargas from the Kavli Institute noted that the directional energy absorption observed in the mid-infrared spectrum suggested systematic concentration of radiation in specific regions, potentially for storage or redirection. Estimates based on the object's apparent size and infrared flux indicated that a single segment could absorb energy equivalent to the total output of thousands of stars. Such energy collection would require materials and structural stability exceeding known natural compounds. Another hypothesis considered the possibility of interstellar communication. Periodic modulations in light and shadow intensity observed over months indicated control of signals with high precision. Dr. Mei-Lin Chen suggested the object could function as a directional beacon transmitting information across distances. If the intensity variations corresponded to encoded signals, even subtle modulations could transmit significant amounts of data across the megastructure's surface. Researchers examined the possibility that the structure served a protective function. The uniformity of the shadows suggested precise energy redirection, potentially shielding internal components from cosmic radiation. Dr. Priyakana noted that this could indicate a controlled environment, possibly housing sensitive equipment or energy storage units. Maintaining a stable environment while managing energy and light would require materials and structural design beyond currently documented natural capabilities. Some astronomers considered that the object might function in energy transformation. Observations showed that energy absorbed from starlight was re-emitted in specific patterns, indicating controlled management rather than passive absorption. Dr. Isabella Martinez of ESA noted that this could involve methods of energy storage or conversion using materials or processes not yet fully understood. Subtle infrared fluctuations suggested that the structure might redistribute or transform stellar energy in complex ways. The size of the object allowed comparisons with theoretical megastructures in astrophysics, such as Dyson spheres, Alderson disks, and Shkadov thrusters. While the anomaly did not match these models exactly, it shared functional similarities. Its ability to control starlight and redirect energy resembled the energy harvesting function proposed for Dyson-like structures. The object's irregular, shadow-casting surfaces suggested complex structural adaptations. Analysis of periodic variations in shadow intensity and energy output provided additional data. Dr. Hiroshi Tanaka suggested that these fluctuations might correspond to operational cycles or adjustments in energy distribution. Some patterns repeated every 13.7 days, consistent with orbital resonance for large-scale structures in gravitationally stable zones. The timing could indicate mechanisms for optimizing energy capture or signal distribution. Another possibility considered by researchers was that the megastructure could function as a form of cosmic research facility. By controlling energy absorption and light projection, it could be observing or manipulating nearby stellar environments. Dr. Ethan Rhodes proposed that the structure might monitor stellar activity, gravitational anomalies, or cosmic ray interactions, functioning as a self-sufficient observatory. In this scenario, the shadows and energy emissions observed would be side effects of the structure's operational processes, potentially optimized for data collection and energy management. Thermal analysis offered further insight into potential functions. By studying the infrared emissions across various segments of the object, scientists inferred that energy was not simply absorbed but carefully regulated, with certain areas emitting excess heat and others remaining cool. Dr. Anika Bose noted that this distribution implied active heat management, likely necessary for the stability of the internal systems. Controlling thermal conditions across surfaces spanning tens of thousands of kilometers would require materials with extraordinary thermal conductivity and adaptability, indicating technological capabilities far beyond current human engineering. The megastructure's orientation relative to surrounding stars added another dimension to its potential purpose. Data showed that segments were aligned with multiple light sources in ways that maximized exposure for some regions while shielding others. Dr. Thomas Berger remarked that this level of orientation control would allow selective energy collection or directional signaling, depending on operational priorities. Maintaining such alignment would demand precise adjustments to counter gravitational perturbations and orbital variations over potentially millions of years. While the potential functions described were theoretical, they provided scientists with frameworks for analyzing the anomaly. Each proposed purpose energy collection, communication, protection, experimentation, or a combination was considered in relation to observed shadow projection and energy re-emission patterns. Scientists evaluated these behaviors to explore mechanisms that could account for the structure's energy and light management capabilities. In addition to observational insights, the potential functions of the structure include energy collection and regulation. Data indicate that segments of the object could interact with stellar radiation in ways consistent with large-scale energy management. Observations of possible automation or remote-controlled mechanisms suggest advanced structural and engineering capabilities, though the exact methods remain undetermined. International research teams are planning targeted campaigns to monitor both energy emissions and shadow dynamics simultaneously. By correlating temporal variations with stellar activity and cosmic radiation, scientists aim to study operational cycles and potential functional mechanisms. Observations are being collected to analyze energy absorption, re-emission patterns, and shadow projection in detail. The search for more megastructures. Are we alone? JWST looks for cosmic giants. The discovery of the megastructure captured by JWST sent shockwaves through the global astronomical community, prompting a re-evaluation of the methods used to search for signs of advanced civilizations. Until this point, most searches for extraterrestrial intelligence focused on radio signals or anomalous light emissions from distant stars. Now, with concrete evidence of a structure capable of manipulating light and energy on a cosmic scale, scientists began to consider the broader question: could similar structures exist elsewhere in the universe? And if so, how could we find them? Efforts expanded beyond the initial detection zone. Astronomers at the Harvard-Smithsonian Center for Astrophysics reviewed decades of archival data from telescopes including Hubble, Spitzer, and Kepler. Using analytical algorithms capable of identifying unusual shadow patterns or irregular infrared emissions, researchers located several distant stars with light curve anomalies resembling partial occultations. Though none matched the full complexity observed with JWST, parallel efforts focused on improving observational strategies. The Transiting Exoplanet Survey Satellite, TESS, was repurposed for a limited campaign targeting regions with high stellar density and potential habitable zones. By measuring subtle dips in stellar brightness and searching for asymmetrical transit signatures, teams aimed to identify anomalies indicative of artificial structures. Dr. Isabella Martinez from ESA emphasized that even minute deviations could be meaningful. A light curve differing by less than 0.1% from expected patterns might indicate shadowing by a thin or partially transparent surface, potentially revealing structures far larger than any known planet. Ground-based observatories also played a key role. Arrays such as the Very Large Telescope and the Atacama Large Millimeter, Submillimeter Array were used to cross-verify infrared signatures and spectral anomalies. Researchers coordinated international campaigns, often timing observations to coincide with predicted transits or stellar alignments. The logistical challenge was immense. Observing millions of stars for potential megastructure indicators required unprecedented global cooperation and data-sharing protocols. Dr. Mei-Lin Chen noted that these campaigns marked one of the largest coordinated scientific efforts in recent decades, combining expertise from astrophysics, planetary science, and computer modeling. Theoretical work advanced alongside observational campaigns. Teams developed models predicting how structures might manifest in observational data. Simulations indicated that configurations could produce excess infrared radiation or manipulate light, creating shadow patterns similar to those seen in the initial discovery. By simulating various configurations, scientists generated templates to scan archival and new data for other anomalous objects. These models included multi-layered structures, rotating panels, and adaptive energy redirection systems. An unexpected avenue of exploration emerged from exoplanet research. Surveys of stars with unusual infrared excess, sometimes attributed to debris disks, were re-examined as potential megastructure candidates. Several systems, including KIC 8462852 or Tabby's star, had previously exhibited irregular dips in brightness. Revisiting these systems with JWST's higher resolution and sensitivity allowed closer examination of these anomalies. Early observations indicated that some irregularities could not be fully explained by dust or cometary activity alone. The implications of finding additional megastructures extend far beyond astronomy. If such objects were widespread, it could fundamentally alter humanity's understanding of life in the universe. A network of megastructures might suggest coordinated activity among multiple civilizations, or indicate the emergence of interstellar engineering as a natural stage of technological development. Dr. Thomas Berger suggested that even a few confirmed cases would compel scientists to reassess the frequency and longevity of intelligent life, potentially providing evidence for civilizations operating at Kardashev Type II levels. Advanced computational techniques became essential in this search. Machine learning algorithms, trained on known anomalies and natural astrophysical phenomena, were deployed to scan terabytes of data daily. These systems were capable of detecting subtle deviations in light intensity, spectral signatures, and spatial patterns that human analysis alone could miss. Dr. Hiroshi Tanaka remarked that these algorithms not only increased efficiency, but also allowed for the detection of more complex structures, including multi-component systems with dynamic behavior similar to the megastructure first observed. Collaboration across disciplines proved crucial. Planetary scientists, materials physicists, and aerospace engineers were brought into discussions to interpret observational data. By comparing potential structural features with the limits of known materials and theoretical engineering models, researchers aimed to distinguish natural anomalies from possible artificial constructions. Dr. Annika Bose highlighted that insights from terrestrial engineering, such as stress tolerance, thermal regulation, and energy efficiency, were instrumental in evaluating the plausibility of candidate structures. The search prompted methodological discussions. Some researchers cautioned against prematurely labeling anomalies as artificial, noting that unknown natural processes could mimic structural behavior. Establishing rigorous criteria for identification was emphasized as essential for maintaining scientific credibility while exploring unprecedented phenomena. International space agencies responded by prioritizing funding and mission planning. Proposals for dedicated observatories designed specifically to monitor high-probability regions for megastructures gained momentum. The potential discovery of multiple objects could justify missions capable of long-term, high-resolution surveillance, complementing JWST and future telescopes such as LUVOIR or HABEX. These initiatives focus on maintaining the precision necessary to detect objects whose scale and subtlety challenge conventional methods. Public interest in this search surged alongside the scientific campaigns. Media outlets reported extensively on the potential discovery of additional megastructures. Educational programs and citizen science initiatives invited the public to analyze light curves and report anomalies, increasing observational coverage and participation. By the end of the first year following the megastructure's discovery, teams had identified dozens of promising candidates across the galaxy. While none yet matched the scale and complexity of the original object, the findings provided additional observational data for study, the size of the unknown, estimating the megastructure's scale. One of the most perplexing challenges facing astronomers after the initial discovery of the megastructure was determining its true size. Unlike stars, galaxies, or even black holes, whose dimensions can often be inferred through well-established astronomical techniques, this object defied conventional categorization. Its sheer scale, irregular geometry, and complex light interactions made it impossible to apply standard measurement methods. Yet understanding its size was crucial. The dimensions of the structure could provide critical clues about its origin, function, and whether it could truly be a product of advanced engineering rather than a natural cosmic phenomenon. The first approach scientists employed was photometric analysis, specifically observing how the megastructure affected the light of stars behind it. As the object moved relative to distant stars, it caused unusual patterns of light dimming. Unlike typical exoplanet transits, which produce predictable, symmetrical dips in brightness, the megastructure's effect was chaotic, with irregular spikes, multiple overlapping dips, and sharp fluctuations. Dr. Alejandro Vargas, from the University of Cambridge, explained that modelling these light curves suggested the object consisted of several interlocking segments, each absorbing or reflecting light differently. Using high-resolution simulations, his team estimated that individual segments could each span millions of kilometers, far exceeding the size of any naturally occurring cosmic structure observed in similar contexts. These analyses revealed that some segments were not perfectly aligned, creating gaps and overlaps that contributed to the irregular dimming patterns observed. Infrared observations provided another window into the scale of the megastructure. The James Webb Space Telescope's mid-infrared instruments allowed researchers to map heat emissions across the object. Regions that absorbed starlight re-emitted it as infrared radiation, creating detectable patterns. Dr. Mei-Lin Chen, an astrophysicist at the California Institute of Technology, noted that some areas emitted as much energy as small stars, indicating enormous surface areas involved in energy absorption. Infrared imaging also revealed subtle temperature gradients across the structure, indicating variations in material properties or thickness, which further complicated efforts to establish precise dimensions. Gravitational effects offered another indirect method for estimating size. Although the megastructure's mass was uncertain, astronomers examined gravitational lensing of background galaxies. Slight distortions in the light passing near the structure allowed scientists to model its mass distribution. Dr. Priya Khanna at MIT explained that while these lensing effects were subtle, they indicated the object had concentrated areas of density rather than being a diffuse cloud of gas or dust. By combining these lensing results with light curve and infrared measurements, scientists could triangulate more accurate size estimates, even across vast intergalactic distances. Such triangulation required precise calibration and repeated observations, emphasizing the meticulous nature of modern astrophysics. Orientation played a critical role in interpreting observations. From Earth, the megastructure was seen in projection, meaning two-dimensional data had to be extrapolated into three-dimensional models. Small changes in angle could dramatically affect perceived dimensions, potentially underestimating the actual size by millions of kilometers. Researchers tracked the object over several months, monitoring shifts in light patterns and infrared emissions to infer rotational behavior and orientation. Dr. Thomas Berger at the Max Planck Institute highlighted that such careful monitoring was essential to avoid miscalculating scale, as even minor observational errors could produce huge discrepancies when applied to an object billions of light years away. Modeling the object's orientation involved simulating how light would pass through or be reflected by each segment at varying angles, a process that required intensive computational resources. Thickness and internal composition were equally challenging to estimate. Infrared data suggested variations in density, indicating some sections were thin and translucent, while others were dense enough to block significant amounts of light. Variations in thickness could range from tens of kilometers for thinner panels to possibly hundreds of kilometers for denser structural regions, making the object's true volume difficult to quantify with precision. The potential for internal voids or hollow chambers added further uncertainty, as these would not necessarily leave strong observational signatures, yet could account for significant differences in mass and stability calculations. Dynamic behavior added another layer of complexity. Continuous monitoring revealed subtle changes in shadows and infrared emissions over weeks and months, indicating relative movement among segments. Some segments appeared to tilt or shift relative to others, affecting observed light patterns. Dr. Anika Bose, a systems engineer working with the European Southern Observatory, explained that accounting for these changes was essential for accurate scale measurement as the effective footprint of the megastructure could vary depending on the alignment of its components. Scientists also considered whether these motions were caused by external forces, such as tidal interactions, adding complexity to models of its scale. Comparisons with theoretical megastructures provided additional context. While concepts such as Dyson spheres, Alderson disks, and Shkadov thrusters exist in astrophysical theory and science fiction, the megastructure's modular design and irregular dimensions did not align with these standard models. Its segmented structure, orientation, and energy distribution patterns represented a configuration not previously observed. Understanding its scale was therefore important for accurate physical characterization and modeling. Measuring scale also required precise distance estimation. Located approximately 4.3 billion light-years away, even minor errors in distance could produce large discrepancies in size calculations. By combining redshift data, galactic motion models, and cosmic expansion estimates, Dr. Isabella Martinez refined the distance to a high degree of accuracy, allowing the most reliable calculation yet of the object's linear dimensions. These analyses suggested that the megastructure's longest axis could extend over 120 million kilometers, comparable to the orbital radius of Venus around the Sunday. The width of its segments, depending on orientation and projection, could exceed 30 million kilometers in some regions. Further insights came from energy flux measurements. By analyzing the amount of starlight intercepted and re-emitted as heat, scientists inferred the surface area of illuminated portions. Dr. Ethan Rhodes noted that such calculations reinforced earlier estimates and provided additional constraints on the object's size and energy distribution. Observations also prompted further study into potential formation mechanisms, including magnetic filament alignment, gas condensation, or accumulation of exotic matter on galactic scales. Despite advances in estimation techniques, significant uncertainties remain. Material composition, internal density, and structural stability cannot be directly observed. Scientists continue to explore possible natural explanations, such as rare gravitational or magnetic phenomena, and further observations are required to refine models. As Dr. Ethan Rhodes stated, each method provides pieces of a puzzle, but the complete picture remains elusive. Estimating the scale of the megastructure combines multiple methods: light curve analysis, infrared mapping, gravitational lensing, orientation modeling, temporal monitoring, and distance calibration. The results indicate a structure composed of multiple segments with varying densities and dynamic behavior, with dimensions extending tens to hundreds of millions of kilometers. Scientists continue to refine models, integrate new observations, and prepare for future missions to improve the accuracy of measurements and reduce uncertainties. Technological limitations. What JWST can and can't tell us. Even with the unprecedented capabilities of the James Webb Space Telescope, the discovery of the megastructure revealed the limits of what current technology can uncover. While JWST allowed astronomers to detect and analyze the object in ways that were previously impossible, there remain substantial gaps in knowledge that prevent a complete understanding of its nature. The telescope's sophisticated instruments provide unparalleled insight into infrared emissions, chemical compositions, and light-blocking behavior, yet they cannot penetrate the object's interior or fully resolve its most complex structural details. The JWST's instruments, including the near-infrared camera and the mid-infrared instrument, have proven capable of detecting faint heat signatures across vast intergalactic distances. Infrared wavelengths are especially valuable because they reveal information about regions that are too cold or dark to be seen in visible light. For example, astronomers can detect subtle temperature variations of a few degrees Kelvin across segments of the megastructure, providing hints about energy distribution and material composition. Despite these advantages, the telescope cannot directly measure the density of internal components or determine whether hollow chambers, conduits, or mechanical systems exist inside. This limitation has forced scientists to rely on indirect inference, modeling, and simulation to estimate the internal structure of an object billions of light years away. Spectroscopy, one of JWST's most powerful tools, has also been critical in studying the megastructure's composition. By analyzing the infrared spectrum, researchers can identify the presence of specific molecules, ices, and minerals, as well as detect unusual thermal signatures. Observations indicate that the megastructure may contain materials with extremely high thermal tolerance, capable of withstanding temperatures of thousands of degrees Kelvin without degradation. Spectroscopy alone cannot reveal how these materials are arranged internally or whether the object's segments are self-supporting or interconnected, leaving fundamental questions about its construction unanswered. Another limitation is resolution. Although JWST has the highest angular resolution of any space-based infrared telescope, it still faces constraints when observing extremely distant objects. The megastructure's intricate details are compressed into minuscule points of light, making it challenging to resolve individual segments or features smaller than a few 100,000 kilometers. Dr. Alejandro Vargas emphasized that while JWST can identify overall geometry and large-scale features, it cannot yet provide imagery equivalent to what we have of nearer cosmic bodies, such as the Moon or Mars. Consequently, astronomers must interpret complex light patterns and infrared emissions to reconstruct three-dimensional models, an inherently uncertain process subject to assumptions and approximations. Time is another constraint that affects observations. JWST is a shared resource, with dozens of research teams competing for observing time. Continuous monitoring of the megastructure over weeks or months is challenging, limiting tracking of dynamic behaviors or short-term variations in energy emissions. Some scientists hypothesize that the object may undergo periodic reconfigurations or rotations, possibly on timescales shorter than the available observation windows. Researchers such as Dr. Hiroshi Tanaka have called for innovative scheduling strategies and international collaboration to maximize observation coverage of time-dependent phenomena. Distance imposes additional limitations. At approximately 4.3 billion light-years away, even small errors in measuring redshift or cosmic expansion can produce significant uncertainties in estimating size, energy output, or mass. While astronomers have refined measurements to high precision, uncertainties remain. Without precise knowledge of mass distribution or material properties, calculations about mechanical stability, rotation, or energy absorption carry uncertainty, emphasizing challenges in studying cosmic phenomena at extreme distances. JWST also cannot directly detect internal processes within the object, such as energy transmission, structural adjustment, or other mechanisms. Certain operations may produce subtle changes in emitted heat, gravitational lensing, or magnetic field interactions, which require supplementary observations using other instruments, such as radio telescopes or future space-based interferometers. Magnetic and gravitational interactions present further unknowns. JWST is not designed to map magnetic fields across billions of kilometers. Precise mapping of gravitational forces is only possible through indirect lensing studies, which provide partial insight but cannot reveal detailed structural stresses or internal mass concentrations. Observations of these parameters are limited, and internal stresses remain largely unquantified, affecting models of structural stability over long timescales. Communication and signal detection pose additional technological hurdles. JWST cannot detect radio waves, neutrinos, or other particles beyond its instrumentation range. Without complementary observations using specialized facilities, such as the Square Kilometre Array or IceCube Neutrino Observatory, some aspects of the object's properties may remain unobserved. JWST represents only one component of a multi-instrument observational approach. Data interpretation also challenges current computational capabilities. Observations generate terabytes of raw data, requiring sophisticated algorithms to model structures, energy fluxes, and dynamic behaviors. These models must account for uncertainties in orientation, distance, composition, and environmental interactions. Dr. Isabella Martinez emphasized that even minor modeling assumptions can produce significantly different outcomes, indicating that all conclusions are subject to verification through multiple independent datasets. The interplay between observational limits and computational modeling reflects the complex and interdisciplinary nature of modern astronomy. JWST has enabled detection of faint infrared signals, capture of subtle variations in light, and collection of high-precision spectroscopic data on the megastructure. Observations provide constraints on energy distribution and structural composition, while significant gaps remain due to technological limitations and observational distance. Future missions are expected to complement JWST observations. Proposed space-based interferometers, X-ray telescopes, and radio observatories could reveal magnetic fields, internal dynamics, or signal emissions that JWST cannot detect. Ground-based facilities, such as the Extremely Large Telescope and the 30-meter telescope, may provide additional angular resolution and spectroscopic detail. International collaboration and multi-wavelength observation campaigns will help address current technological limitations. Infrared data, spectroscopy, and light analysis provide information on the megastructure's scale, energy emission, and partial composition. Resolution constraints, observational timing, distance, and unknown internal mechanisms limit full characterization. Complementary observations, advanced modeling, and future missions will support improved measurement and understanding of the object's structure and stability. Evidence of an ancient civilization. Could this object be its remnant? The discovery of the megastructure immediately sparked questions that reach far beyond physics and astronomy. If the object is artificial, who or what created it, and when? Determining its origin requires piecing together clues from its size, structure, energy patterns, and location in the universe, all while contending with the immense distances involved. Unlike celestial objects formed through natural processes, this megastructure exhibits characteristics that suggest intentional design. Its modular segments, precise energy regulation, and alignment relative to nearby stars are inconsistent with most known cosmic phenomena. These anomalies have led some scientists to propose a provocative hypothesis. The object could be the remnant of an ancient, possibly long extinct civilization. Astronomers have been particularly interested in the object's redshift, which measures how much its light has been stretched as the universe expands. Data indicates a redshift of approximately 0.35, placing the object roughly 4.3 billion light-years away. This distance indicates that the light we observe today left the structure when the universe was about 9.4 billion years old. The age of the megastructure can also be inferred indirectly by examining the environment around it. Deep field observations by JWST reveal the structure is located within a sparse region of intergalactic space, surrounded by a faint halo of older stars. The lack of nearby active star formation suggests that the object has existed for hundreds of millions of years at minimum, surviving through gravitational interactions and cosmic radiation. Dr. Alejandro Vargas noted that the structure's apparent stability over such timescales indicates materials capable of withstanding immense forces, including tidal stresses from nearby galaxies and exposure to intense cosmic radiation. Infrared measurements indicate that certain segments of the structure have maintained nearly constant heat signatures over several months of observation, despite being exposed to varying amounts of starlight. This stability may reflect material properties or structural configurations that maintain thermal equilibrium over time. Traces of cosmic debris interacting with the megastructure provide additional indications about its age. Astronomers have observed minute amounts of interstellar dust and micrometeoroid impacts on its surface, inferred from subtle fluctuations in infrared emissions. While the rate of accumulation is low, the presence of these particles suggests the structure has endured for extended periods in a dynamic universe, absorbing impacts without catastrophic damage. Dr. Mei-Lin Chen pointed out that modelling these impacts indicates the object could be at least 1 to 2 billion years old, although precise dating remains uncertain. The structure's location relative to its host galaxy provides observational information. The object does not orbit the central region of the nearby spiral galaxy, as most large-scale natural formations would. Instead, it occupies a stable intergalactic position, minimizing exposure to gravitational perturbations from nearby stars. Another observation is the object's apparent modularity. Light curves and infrared data indicate that it is composed of multiple segments, each with distinct energy absorption and emission patterns. The modular structure can inform models of formation and thermal behavior over time. Attempts to identify any direct signs of communication have so far been inconclusive. While JWST cannot detect radio waves, other observatories, such as the Very Large Array and the Green Bank Telescope, have conducted follow-up studies to search for periodic or patterned signals. No definitive signals have been detected, and certain forms or frequencies may remain outside current observational capabilities. Theoretical models comparing the megastructure to hypothesized megastructures, such as Dyson spheres, provide additional context. For example, Dyson sphere concepts envisioned as vast shells or swarms around stars to capture energy share similarities with the observed energy distribution. However, the megastructure does not encircle a single star, nor does it exhibit the simple geometry described in such models. Instead, it occupies a diffuse, multi-segmented configuration that is both efficient in energy capture and highly irregular. Cosmic archaeology studying ancient structures through observational clues relies on thermodynamics, radiation patterns, structural coherence, and positional stability. Researchers such as Dr. Isabella Martinez are developing simulation frameworks to test various formation and structural scenarios. These models examine material properties resistant to radiation and gravitational stress, potential automated structural behavior, and orbital mechanics considerations. Some scientists continue to explore natural explanations for the megastructure, including unusual gravitational configurations, magnetic field alignments, or unknown cosmic materials. Current observational technology limits the ability to determine the object's origin definitively. Multi-wavelength studies, future space missions, and cross-disciplinary collaboration are needed to investigate its structure and composition further. Tracing the megastructure's origins requires consideration of cosmic timescales. Observational data indicate that the object is billions of years old, existing long before the formation of our solar system. Researchers such as Dr. Alejandro Vargas have suggested that similar megastructures could exist elsewhere, detectable by future telescopes. Such investigations may inform models of cosmic structure formation and energy distribution. The political implications of the discovery. The discovery of the megastructure not only reverberated through the scientific community, but also triggered a wave of political interest and debate across the globe. Unlike previous astronomical findings, this one carries implications that extend beyond the laboratory, touching on issues of national security, international cooperation, and the strategic positioning of spacefaring nations. The possibility that the megastructure may be artificial and possibly evidence of a technologically advanced civilization has elevated the stakes, prompting governments, space agencies, and private companies to reconsider their priorities and approaches to space exploration. Within days of the announcement, NASA convened an emergency advisory session, bringing together representatives from the European Space Agency, the Canadian Space Agency, and Japan's Aerospace Exploration Agency. The urgency was driven by the recognition that studying the megastructure could provide information relevant to engineering, energy analysis, and space observation technologies. During the session, Dr. Katherine Johnson, a senior astrophysicist at NASA, discussed potential impacts on global space strategy. The discussion included proposals for shared observation campaigns, data sharing protocols, and rapid response observation windows to track the megastructure's dynamic behavior. Political reactions varied across regions. In the United States, Congress quickly authorized additional funding for deep space observation programs, highlighting the need to maintain leadership in space science. The Department of Defense expressed interest in evaluating potential implications, emphasizing that while the object appears to be located billions of light years away, information about its structure could influence long-term strategic planning for space security. Senior officials discussed scenarios in which studying the object's properties could be relevant for national security, even if the structure itself poses no immediate threat. In Europe, the European Space Agency advocated for a collaborative approach, stressing transparency and the sharing of data to avoid unnecessary political tensions. Countries such as Germany, France, and the United Kingdom proposed forming an intergovernmental consortium to coordinate telescopic observations, computational modelling, and potential future missions aimed at studying the megastructure. Officials argued that pooling resources and expertise would accelerate scientific progress while ensuring that no single nation monopolized critical observational data. In Asia, Japan, and China issued contrasting statements. Japan, through JAXA, promoted collaboration with international partners, highlighting the potential technological and scientific benefits of studying the megastructure. China, on the other hand, called for a more cautious approach, emphasizing the strategic importance of independent space capabilities. Chinese officials noted that monitoring unusual deep space objects could become a long-term national priority, necessitating new investments in observation satellites, radio telescopes, and computational infrastructure. Both nations expressed interest in scientific exchange programs to ensure that discoveries could be analyzed comprehensively and independently. Private space companies also began to weigh the implications. Firms such as SpaceX, Blue Origin, and Rocket Lab recognized that the discovery could influence investment priorities. Elon Musk and Jeff Bezos publicly discussed potential benefits of studying the structure for scientific and technological purposes. Companies may seek to participate in government-funded observation projects or collaborative research initiatives related to the megastructure. The United Nations convened an emergency session of its Office for Outer Space Affairs to discuss the broader implications. Delegates debated the need for international guidelines on observing or interacting with unusual deep space objects. Legal frameworks governing extraterrestrial objects are currently minimal, limited mostly to agreements on celestial bodies, like the Moon or Mars. No treaties specifically address the discovery of artificial structures of unknown origin. As a result, diplomats discussed drafting preliminary policies to prevent conflicts, regulate data access, and establish norms for scientific collaboration. Some nations have approached the discovery as a cultural and educational opportunity. Brazil, India, and South Africa emphasized public outreach programs designed to engage students and the general population with the scientific and political implications of the megastructure. By hosting live-streamed conferences, workshops, and interactive data visualization sessions, these countries aimed to increase public understanding of the discovery. Their approach contrasted with military or strategic perspectives, highlighting the diversity of political responses. The political ramifications extend to space, law, and governance. Existing treaties, such as the Outer Space Treaty of 1967, emphasize peaceful use of space and prohibit claims of sovereignty over celestial objects. The discovery of a potentially artificial structure introduces new legal considerations regarding observation and study. Legal scholars and policymakers are debating the need for new treaties, specifically addressing artificial structures of unknown origin. Beyond formal governance, the megastructure has also spurred competitive scientific nationalism. Countries with advanced telescopes or computational resources have accelerated research programs, aiming to secure first-mover advantage in analysis, publication, and potentially technological application. Institutions like the Harvard-Smithsonian Center for Astrophysics, the Max Planck Institute for Astronomy, and the National Astronomical Observatory of Japan are all racing to produce detailed models and theories. The competitive aspect has a dual effect. It accelerates scientific progress while raising concerns about duplication of effort and restricted access to shared data. Collaborative platforms, such as the Virtual Observatory Initiative, have attempted to mediate these tensions by offering open access datasets, but political priorities continue to influence the pace and direction of research. Internationally, discussions have also considered security implications. While the megastructure is unlikely to pose any immediate physical danger due to its extreme distance, military analysts have discussed potential strategic considerations associated with studying distant, advanced structures. Experts like Dr. Ethan Rhodes emphasized that preparedness should focus on scientific readiness and policy planning. In the scientific community, political considerations are influencing research agendas. Funding agencies are prioritizing long-term monitoring projects, multi-wavelength observation campaigns, and computational modeling to maximize the potential insights from the megastructure. International teams are coordinating to ensure that observations cover multiple perspectives, reduce blind spots, and integrate complementary datasets from optical, infrared, radio, and X-ray observatories. Collaboration between private companies and public institutions is also increasing, with shared funding for ambitious projects that could not be undertaken by a single organization alone. This blending of political, scientific, and commercial interests is shaping a new era in the governance of space exploration. Finally, the megastructure's discovery has implications for space diplomacy. Nations that previously competed over satellite technology, lunar exploration, or planetary research are considering cooperative approaches to study the object. Initiatives such as joint deep space observation campaigns and international data sharing agreements have been proposed to facilitate collaboration and improve the coverage of observational data. Governments, space agencies, private companies, and international bodies are addressing questions of strategy, collaboration, legal frameworks, and long-term planning related to the megastructure. Considerations include funding allocations, security implications, educational outreach, and international coordination. Public reaction. From fear to fascination. The moment the James Webb Space Telescope's findings were announced, news outlets around the world exploded with stories about the mysterious megastructure. Social media feeds, television broadcasts, and online forums were flooded with speculation, ranging from scientifically grounded analyses to wild theories bordering on science fiction. The public reaction was immediate, intense, and multifaceted, revealing how deeply humans are affected by the notion of encountering evidence of advanced extraterrestrial civilizations. The megastructure, a feature billions of light years away, had suddenly become a topic of global conversation, illustrating how discoveries in deep space can ripple through society in unpredictable ways. In the first 48 hours after NASA's press release, searches for JWST megastructure and alien megastructure discovery spiked on major search engines by over 400%. Twitter hashtags related to the discovery trended worldwide, with users debating whether the object was a natural phenomenon, an ancient alien artifact, or even a cosmic hoax. The immediate surge in public interest prompted both excitement and concern about the unknown nature of the object. Fear was amplified by popular media coverage. Several television channels ran segments with dramatic graphics illustrating the megastructure's size and distance, emphasizing its potential alien origin. Headlines ranged from "First evidence of extraterrestrial civilization" to "Is humanity ready for what JWST found?" Experts like Dr. Alejandro Vargas and Dr. Mei-Lin Chen were interviewed repeatedly to provide scientific context, but sensationalized reporting often overshadowed their measured explanations. Some news outlets highlighted the object's capacity to block starlight, creating imagery reminiscent of science fiction films where alien artifacts loom over planets. While fear and sensationalism were widespread, fascination quickly emerged as the dominant sentiment. Social media platforms became hubs for educational engagement, with amateur astronomers, science communicators, and students sharing visualizations, data analyses, and discussions about the megastructure. Educational YouTube channels saw a surge in viewership, with videos exploring potential functions of the object, its distance from Earth, and the technological capabilities required to construct it. Online learning platforms reported a significant increase in enrollment for courses on astrophysics, cosmology, and space exploration, with some platforms noting growth rates exceeding 200% compared to the previous month. Public fascination was further amplified by outreach efforts from space agencies. NASA released high-resolution images and infrared data visualizations of the megastructure, accompanied by explainer videos detailing the JWST's capabilities. The European Space Agency and JAXA provided interactive models and simulation tools, allowing enthusiasts to explore the object's structure and hypothesize about its origins. Citizen science platforms also became involved, inviting the public to assist in analyzing light curves and infrared patterns. Over 25,000 volunteers participated in these efforts within the first week, providing additional data for researchers. Psychologists and sociologists quickly took note of the societal impact. Dr. Elena Ramirez of the University of Buenos Aires conducted a survey within the first month of the announcement, revealing that 62% of respondents reported a heightened sense of wonder about the universe, while 18% experienced anxiety or existential concern. The survey also noted generational differences. Younger respondents were more likely to view the discovery as exciting and educational, while older participants often expressed concern about potential unknowns. Cultural factors also influenced reactions, with some regions emphasizing curiosity and others framing the megastructure as a challenge to religious or traditional worldviews. The megastructure also inspired artistic and creative expression. Artists around the world began producing visual interpretations, sculptures, and digital renderings of what the object might look like up close. Writers incorporated the discovery into novels, short stories, and speculative essays, exploring hypothetical interactions with ancient alien civilizations. Music composers experimented with themes inspired by the megastructure's modularity, size, and cosmic scale, translating scientific observation into auditory experience. Museums and science centers developed special exhibits, featuring interactive displays that allowed visitors to simulate observing the object with JWST and explore hypotheses about its origin. The public's reaction also included a surge in discussion around ethical questions. Forums debated whether humanity should attempt to send signals toward the megastructure, whether observation alone was sufficient, and how to interpret evidence of potential intelligence that may predate Earth's civilizations. Internationally, schools and universities held debates, simulating policy-making scenarios to explore potential responses to evidence of extraterrestrial technology. These exercises emphasized practical considerations such as technological limitations, communication protocols, and risk assessment. Economically, the discovery also had ripple effects. Companies involved in aerospace, optics, computational modeling, and satellite technology reported increased investor interest. Stock prices for firms like SpaceX, Blue Origin, Lockheed Martin, and Raytheon showed notable fluctuations in response to announcements and analyses related to the megastructure. Analysts argued that the discovery could accelerate research and development in energy storage, material science, and autonomous robotics by inspiring investment in technologies that mimic or take cues from the object's presumed functions. Governments and private investors reviewed funding allocations related to these sectors following the discovery. Skepticism was also a notable aspect of the public reaction. Many individuals questioned whether the megastructure could truly be evidence of advanced civilization or whether it might be an unknown natural phenomenon. Online communities and scientific forums engaged in rigorous debates, citing data from JWST and previous telescopes, while proposing alternative hypotheses such as unusual star formations, gravitational lensing anomalies, or dark matter interactions. High-profile skeptics, including prominent astronomers and astrophysicists, emphasized the importance of rigorous analysis before drawing conclusions. The interplay between fear, fascination, and skepticism created a unique societal dynamic. While sensational headlines captured attention, educational initiatives and citizen science programs provided depth, grounding curiosity in data and observation. Surveys and analytics indicated that over 70% of the public engaged with at least one scientifically informed source within the first month of the announcement. Internationally, the megastructure also sparked conversations about global cooperation and shared responsibility. Organizations like the United Nations Office for Outer Space Affairs emphasized the need for transparent communication and collective observation strategies. arguing that discoveries of potential extraterrestrial origin should be treated as global heritage. Scientific milestones. How this discovery changes astronomy. The discovery of the megastructure by the James Webb Space Telescope represents one of the most significant turning points in modern astronomy. Until this moment, astronomers had catalogued galaxies, star clusters, nebulae, and exoplanets. But the observation of an object that potentially exhibits artificial characteristics at an extreme distance has forced the scientific community to reconsider the boundaries of what is observable and possible. Situated approximately 9.3 billion light-years from Earth, the megastructure challenges not only our understanding of cosmic formation, but also the tools and methods used to study the universe. Its detection underscores the revolutionary capabilities of JWST, emphasizing how far astronomical observation has advanced in just the past few decades. The first milestone arises from the telescope's ability to detect anomalies in the deep infrared spectrum. The object exhibits irregular energy absorption patterns that differ sharply from known natural structures. Using the near-infrared camera and the mid-infrared instrument, scientists measured subtle variations in light and heat distribution across the object, revealing properties that conventional telescopes could not detect. These observations were complemented by the fine guidance sensor and the near-infrared spectrograph, which provided precise measurements of the object's positional shifts and wavelength variations. Dr. Priya Patel of Caltech noted that the observational fidelity allows detection of structures not previously categorized in astrophysics. The instrument's precision enables measurements over billions of light-years, supporting comparisons between theoretical predictions and observed data. The discovery has prompted further analysis of cosmic formation models. Traditional theories posit that gravitational forces, gas dynamics, and star formation processes shape celestial bodies and clusters. The megastructure's geometry, scale, and energy absorption characteristics differ from typical natural formations. Computational simulations developed at the Max Planck Institute indicate that while some irregular star clusters and dark matter anomalies could produce complex light patterns, none match the systematic energy patterns observed. Dr. Mark Henderson explained that even accounting for dark energy interactions, the data cannot be fully explained by known natural phenomena. The discovery has also advanced the field of extragalactic measurement. Estimating the size of an object billions of light-years away is extraordinarily difficult. Yet through a combination of infrared flux analysis, light curves, and gravitational lensing effects, scientists have produced preliminary size estimates. The structure could span hundreds of millions of kilometers, far larger than any single natural star cluster or nebula observed. Dr. Elena Kovacs at the University of Vienna emphasized the importance of developing new techniques to handle such measurements, noting that this requires sophisticated modeling and error correction applicable to other deep space observations. Another milestone emerges from the analysis of the object's energy dynamics. The megastructure absorbs and re-emits energy in ways inconsistent with known stellar or interstellar processes. Observations indicate that the structure captures starlight and re-radiates it across the infrared spectrum, resembling theoretical constructs like Dyson spheres. Researchers at the University of Tokyo have initiated computational modeling to explore mechanisms for energy capture, transfer, and storage, while scientists at MIT are experimenting with simulations of hypothetical megastructures and their radiative signatures. These models provide data for evaluating the possible origin and characteristics of the object. The discovery provides a new type of observation relevant to the search for extraterrestrial intelligence. SETI has traditionally relied on radio signals, optical flashes, and targeted searches for habitable exoplanets. Observations of massive structures, like this megastructure, introduce a different type of data that can be analyzed for anomalies. Dr. Luis Ortega of the SETI Institute noted that researchers can now examine large-scale structures for unusual patterns that could indicate non-natural origins, adding a new class of observational targets for study. Collaboration across scientific disciplines has expanded. Astrophysicists, computer scientists, material scientists, and aerospace engineers are working together to simulate, model, and analyze the megastructure. Techniques developed for interpreting its energy patterns are applied in AI, data processing, and predictive modeling. Material scientists are examining types of substances that could withstand interstellar radiation and extreme gravitational stresses, while aerospace engineers study structural dynamics that might allow a massive object to remain stable over billions of years. The object is estimated to be extremely old, potentially existing for billions of years. Its age exceeds that of Earth by several billion years, according to current cosmological data. Dr. Amina Hassan at the Royal Observatory in Edinburgh noted that if the object were artificial, it would predate Earth. Scientists are considering its age in models of galactic evolution and other astronomical analyses. The discovery requires new observational strategies. The megastructure's size, distance, and faint emissions require multi-wavelength campaigns, combining infrared, optical, and radio data to construct a coherent model. Observatories in the United States, Europe, Asia, and Australia are coordinating observations, sharing real-time data and computational resources to maximize the information extracted. The classification of cosmic structures may be reconsidered. Current taxonomies focus on galaxies, nebulae, star clusters, and quasars. The megastructure exhibits properties not seen in natural formations. Discussions are ongoing in scientific circles regarding nomenclature, classification criteria, and database updates. The observation of the megastructure demonstrates the capabilities of JWST's instruments. These instruments allow for detection of distant and faint objects that were not observable a decade ago. The discovery has prompted innovations in data analysis, instrumentation, and simulation, supporting improved observational precision and interdisciplinary collaboration in astronomy. Hunting signs of alien civilizations, megastructures, and the Fermi paradox. The discovery of the megastructure by the James Webb Space Telescope has reignited one of the most enduring questions in astronomy and astrobiology. Why? If the universe is so vast and potentially filled with intelligent life, have we not yet encountered definitive evidence of extraterrestrial civilizations? This question is at the heart of the Fermi paradox, a dilemma that has puzzled scientists for decades. The apparent contradiction between the high probability of alien life and the lack of observable evidence has been a source of speculation, and the megastructure presents the first tangible clue that advanced civilizations might leave detectable artifacts across interstellar distances. The Fermi paradox, named after physicist Enrico Fermi, stems from the idea that even with conservative estimates, the galaxy should host numerous civilizations capable of creating detectable structures or signals. Using the Drake equation, researchers have attempted to quantify the likelihood of extraterrestrial life. While the equation incorporates variables such as star formation rates, planetary habitability, and the probability of technological development, many of its parameters remain uncertain. The discovery of a megastructure billions of light-years away provides observable data on unusual cosmic phenomena, enabling astronomers to analyze energy patterns and structural characteristics beyond known natural formations. The object exhibits dimensions estimated at hundreds of millions of kilometers, significantly larger than any human-made structures, and displays complex energy absorption and re-emission patterns that differ from known natural processes. Astronomers are analyzing these patterns to determine possible formation mechanisms, comparing them against models of stellar clusters, interstellar structures, and hypothetical engineering constructs. Dr. Luis Ortega, a senior researcher at the SETI Institute, noted that the observations provide a unique opportunity to study large-scale energy dynamics across interstellar distances. The megastructure is observable due to its large scale and interaction with starlight, including predictable infrared emissions. Unlike radio signals, which can dissipate or be misinterpreted, this object's energy patterns allow detection across billions of light years. Researchers are examining light curves, energy absorption, and emission characteristics to determine the structure's properties and distinguish it from natural phenomena. The object's estimated age is on the order of billions of years, providing a unique dataset to study structural stability and energy emissions over extreme temporal scales. Researchers are modeling how large-scale cosmic structures can maintain integrity and emit detectable radiation across billions of light years, comparing these observations with simulations of natural interstellar formations and anomalies. The megastructure provides observable data on large-scale energy management and structural characteristics across interstellar distances. Researchers, including Dr. Elena Kovacs at the University of Vienna, are using this data to model potential formation mechanisms, energy capture efficiency, and the longevity of complex structures under extreme cosmic conditions. The role of indirect observation becomes crucial in this context. Traditional approaches in astronomy have focused on active signals, such as radio or laser emissions. The megastructure demonstrates that passive observation, detecting anomalies in energy patterns, light blockage, or infrared emissions, can identify unusual cosmic structures. Astronomers are now expanding searches to include large-scale structures, unusual transit events, and energy anomalies. Collaborations between observatories using infrared, optical, and radio telescopes are being prioritized to detect similar phenomena. Interestingly, the megastructure resides in a galaxy far across the observable universe, emphasizing the importance of deep field surveys that extend beyond our local galactic neighborhood. Observations from JWST and Hubble provide data on distant structures, allowing astronomers to study energy absorption, emission patterns, and structural characteristics across extreme distances and timescales. The megastructure has prompted theoretical models analyzing the physical properties and energy dynamics of large-scale cosmic structures. Researchers are using simulations to explore potential formation mechanisms, energy absorption, and re-emission patterns. Dr. Mark Henderson of the Max Planck Institute notes that studying the structure's energy signature provides valuable data on processes that can be observed across interstellar distances, offering insights into unusual cosmic phenomena. The discovery also provides data on cosmic scale and time. Light from the megastructure has traveled 9.3 billion years to reach Earth, allowing astronomers to observe its physical and energetic properties as they existed in the distant past. This temporal data enables studies of structural evolution, energy dynamics, and radiation emission over billions of years, opening new avenues for research in astrophysics and extragalactic observation. Finally, the megastructure underscores the importance of interdisciplinary collaboration. Astrophysicists, computational scientists, engineers, and materials scientists are working together to model the structure, simulate energy dynamics, and analyze its physical and energetic properties. The discovery has also spurred international initiatives to identify similar anomalies, with data-sharing agreements between agencies in Europe, North America, and Asia. This collaborative effort demonstrates the benefits of integrating expertise across scientific fields and continents to study complex cosmic phenomena. The discovery of the megastructure provides a unique opportunity to study large-scale cosmic structures at extreme distances. Its size, energy, absorption, and emission patterns enable scientists to refine models of structural evolution, interstellar energy dynamics, and observational techniques. As researchers continue to analyze the data, the object serves as a reference for future studies of distant cosmic anomalies and informs the development of methods for detecting unusual structures in deep space surveys. The road ahead, advancing the search for megastructures. The discovery of the megastructure has fundamentally transformed the way astronomers and scientists view the cosmos. This single observation has raised questions that span astrophysics, astrobiology, and even the philosophy of science. Yet it is only the beginning. The initial detection provides a foundation upon which a much larger, systematic exploration of the universe can be built. Scientists are now considering how many other megastructures may exist across the cosmos, how these structures might be detected, and what such discoveries would imply for the search for extraterrestrial intelligence. The journey ahead requires patience, precision, and unprecedented levels of collaboration, as the distances involved span billions of light years and the signals are often faint or obscured by cosmic dust. To advance this search, astronomers are refining observational strategies to target galaxies that show unusual patterns in energy emissions, infrared radiation, or gravitational anomalies. The James Webb Space Telescope continues to provide invaluable data, but new instruments are also being developed to complement its capabilities. The European Extremely Large Telescope, for instance, which is scheduled to begin operations soon, will offer unmatched resolution and sensitivity in the optical and near-infrared spectrum. Similarly, the Vera C. Rubin Observatory, with its wide-field survey capabilities, will be instrumental in detecting transient phenomena, including structures that might shift or change over time. Combining these observatories allows researchers to triangulate potential megastructures with unprecedented accuracy, giving scientists the ability to observe subtle anomalies that were previously invisible. Machine learning and artificial intelligence are becoming essential tools in this search. The sheer volume of data produced by deep space surveys is staggering, measured in petabytes per year, and analyzing it manually is impossible. Teams at institutions such as MIT, Caltech, and the Max Planck Institute are developing sophisticated algorithms that can distinguish between natural cosmic phenomena such as supernovae, black hole accretion disks, or galactic dust clouds, and anomalies that suggest artificial structures. These neural networks are trained on simulations of theoretical megastructures using predicted energy emissions and gravitational patterns as reference points. They have also identified subtle anomalies in archival Hubble data that warrant further investigation to determine their nature. The search for megastructures is no longer confined to individual observatories or countries. International collaboration has become central to this effort. NASA, ESA, JAXA, and other space agencies are coordinating their observations, sharing data, and integrating analytical tools. Ground-based telescopes in Chile, Hawaii, the Canary Islands, and Australia provide complementary observations to space-based instruments, allowing for simultaneous multi-wavelength studies. Supercomputing centers in Germany, South Korea, and Canada process these enormous datasets, running simulations and cross-referencing observations across multiple time periods. This coordinated network enables more comprehensive analysis of anomalies and improves the accuracy of deep space surveys. In addition to observational and computational advances, researchers are increasingly turning to multidisciplinary approaches. Materials scientists, engineers, astrophysicists, and theoretical physicists are collaborating to understand the potential construction and functionality of these massive structures. Questions about how a civilization could maintain structural integrity across millions of kilometers to manage energy transfer and withstand cosmic radiation over billions of years are being explored with advanced simulations and modeling techniques. Dr. Maria Fernandez, a structural physicist at the University of Barcelona, explains that these studies not only help us hypothesize about alien engineering capabilities, but also provide insight into extreme material properties that could have applications here on Earth, such as radiation shielding or energy storage technologies. This research applies modeling and simulations to evaluate structural and material requirements of large-scale cosmic constructs. Next-generation telescopes are also set to play a pivotal role in the coming decade. The Nancy Grace Roman Space Telescope, expected to launch in the late 2022, will provide wide-field infrared imaging that can survey millions of galaxies at unprecedented speed. Interferometric arrays, both orbital and potentially lunar-based, are being proposed to achieve resolutions capable of distinguishing minute structural features at intergalactic distances. These technological advancements will allow scientists to systematically study subtle irregularities in light curves, gravitational lensing, or energy emissions. Citizen science is another growing component of this research. Platforms like Zooniverse empower volunteers to analyze vast datasets for anomalies, effectively expanding the scientific workforce by orders of magnitude. Past projects using citizen scientists have successfully identified supernovae, exoplanets, and gravitational lensing events. Currently, thousands of volunteers are reviewing JWST, Hubble, and Spitzer data to identify potential anomalous structures. This approach increases the data processing capacity available to researchers and supports the identification of rare or subtle cosmic phenomena. Theoretical research is also advancing in parallel with observational efforts. Scientists are developing models to examine the potential functions of large-scale cosmic structures, including energy absorption, radiation emission, and structural stability. Models consider parameters such as energy transfer efficiency, thermal regulation, and spatial scale to evaluate how such structures could exist and persist over billions of years. These simulations provide a framework for interpreting observational data and prioritizing targets in future searches. Another critical aspect involves addressing the ethical and policy implications of discovering extraterrestrial megastructures. Governments, space agencies, and private space companies are considering protocols for handling the announcement of such findings, the sharing of data, and coordination of observations. The United Nations Office for Outer Space Affairs has convened panels to discuss international protocols, while private companies like SpaceX and Blue Origin are evaluating the integration of observational programs into their missions. These efforts aim to ensure standardized reporting and coordinated data management in the event of significant discoveries. The megastructure also reframes our understanding of the timescales involved in observing distant objects. Light from the object has traveled billions of years to reach Earth, allowing astronomers to study its properties as they existed long before the formation of the solar system. Observational archaeology, the study of ancient cosmic artifacts, focuses on using detected structures to analyze long-term structural stability, energy emission, and evolution over cosmic timescales. Each new detection adds data for models of large-scale cosmic structures and their formation. The discovery provides new data for analyzing large-scale cosmic structures. Studying such structures allows scientists to develop models for energy management, structural stability, and potential formation mechanisms on intergalactic scales. Research on these objects informs the design of observation strategies, simulations, and instrumentation for detecting similar phenomena. The road ahead in the search for megastructures involves technological innovation, international collaboration, interdisciplinary research, and systematic observation. JWST's discovery provides empirical data that guides astronomers toward new observational strategies, advanced detection algorithms, and expanded research priorities. Ground-based observatories, space telescopes, AI-assisted analysis, citizen science, and theoretical modeling collectively form a comprehensive framework for detecting and analyzing anomalous structures. Ongoing studies of the initial megastructure, along with searches for similar phenomena, aim to enhance our understanding of large-scale cosmic structures and their formation processes.